right, plus n minus 1 on the left, 0 on the right. Take them all and divide them by n. Well, what we're doing here, basically, is we're looking with equal probability at every single possible partitioning. For example, if the pivot stays in position number 1, then the left part will have no elements in it, and the right part would have n minus 1. If the pivot goes into position 1, position 2 rather, then the left will have 1 element to quicksort, and n minus 2. So what we're doing is looking at all the possible splits. So we're looking at the pivot that goes from here to here, then we got 1 and n minus 2. If it goes here, we have 2 and n minus 3. If it goes to here, we have 4, and you get the idea? So we're basically taking the pivot in every single position, adding those costs, because the pivot here means that the cost for the next level is here and here. The pivot is here, the cost for the next level is here and here. So we're taking all those possible ones and we're dividing them by n. Dividing them all by n is like multiplying each of them by 1 over n. That's the probability. So we're evenly counting their possible costs. So the average number of comparisons for n elements in quicksort is equal recursively to the recursive average number of elements for any split that can happen given the equal probability. Plus n plus 1. What is n plus 1? That's the what? That's the f of n. That's the what? That's the actual cost. That's the cost of partition. That's all it is. Okay, so n is, so you can see what's going on here. So now, so this is our equation. Now if you notice here that we have C0, Cn minus 1, but that's really the same cost as Cn minus 1, C0. You can see basically this is going from C0, C1, C2, C3, n minus 1, and this is going from n minus 1, n minus 2, n minus 3, n minus k, eventually n minus n. This is decreasing. But as this is going on, these two are the same, and these two are the same. So we have some matches. So what we can do is we can simply say, we notice that we can take away all the parentheses actually. Because this is just addition, so this plus this plus this plus this. Just take all the parentheses. You'll notice that you have 2 C0s, you'll have 2 Cn minus 1, you have 2 C1s, etc., etc., etc. So therefore you have n plus 1 actual cost plus twice all of them divided by n. Just simplifying it. If I multiply both sides by n, I'm going to get n times Cn, and n times all of this is going to be n times n plus 1, plus multiplying all of this by n gets rid of the n in the denominator, and I have this, n Cn is equal to n plus 1 plus 2 times the sum of all the average costs. Okay. So now what we're going to do is we are going to actually substitute. If you look over here, we're going to replace the value of n with n minus 1. So it's going to be, why? Because we can. Because n is a general number of elements, so therefore n minus 1 could also be used as a value for n. So therefore we're going to write this equation with n minus 1, Cn minus 1, n minus 1, times n, 2 times C0, 1 all the way up to n minus 2. And that's what we're going to do. And so basically what we have here is we subtract this. So this is the original one, and Cn is equal to this, plus this, and I'm going to subtract the version of this one minus this one. Simplify. So when I do that, it gets a little bit messy here. We get n Cn minus n minus 1, Cn minus 1 is finally equal to n times n plus 1 minus, because we have a lot of telescoping subtractions here. That's why we always do subtraction, so we can simplify things. N times n minus 1 minus n minus 1 times n plus 2 times C of n minus 1. So now we have this expression, okay? And then this can be combined. Notice that we have n times n plus 1 minus n minus 1 times n, so this can be multiplied combined. We get 2Cn minus 1, and all of this just becomes 2n. So now we can simplify it some more, and then we solve for n Cn. It's equal to this, and then we simplify again. because we have Cn minus 1 and 2 more Cn minus 1, so it's n plus 1, Cn minus 1 plus 2n. So now we have a formula for NCN. We're still solving for Cn. We're still solving for NCN. So now, we're going to take this formula that we came up with and divide both sides by n times n plus 1, which, by the way, this is the n is the n plus 1. If we divide by n times n plus 1, here the n's will cancel and you'll leave an n plus 1. If you divide this term, the n plus 1 will cancel and you'll have n. And if I divide this one by n times n plus 1, the n's will cancel and you get 2 over n plus 1. So you get this expression. So this is just an expression. Okay, so what are we going to do with this expression? We're going to take this expression, which is Cn over n plus 1, is equal to Cn minus 1 over n. Notice that this is like a recurrence here. So what I can do is I can take, notice that this is n. So this is the expression for n. C of n, if you will, is C of n over n plus 1 plus this plus this. If I substitute n minus 1 here, I'll get C of n minus 1. I'll get n minus 1 plus 1, which is n. I'll get n minus 1 minus 1, which is n minus 2. I'll get n minus 1, and I'll get n minus 1 plus 1, which is n. So I'm substituting for this term the value of this whole thing when n is switched to n minus 1. And it gives me this. This right here. Okay? And so we have this one, and then we just simply extend the bracket for this one. Like that. So now what we're going to do is we're going to repeat this again. This is kind of like a repeated substitution on steroids, you know, a little more advanced version of it. And we'll repeat this the maximum number of times, and you'll see that basically we're going to C of n over n plus 1 is going to be 2 times 1 plus 1 half plus 1/3, etc., plus 1 over n. Multiplying by n plus 1, we have Cn is equal to 2 times n plus 1 plus this summation. This summation is looking like something we might be able to solve. You know what kind of sequence this is? 1 plus 1 half plus 1/3 plus 1/4. It's not geometric because there's no ratio. There's another name for it. Do we know what it is? We did it in class. Harmonic. Remember that? Harmonic here. Say h of n, or harmonic series. So harmonic series is basically this one. And we did harmonic series in class, and we find out the upper bound of the harmonic series using an integral. The summation of 1 over I, as I goes from 1 to n. Now, 1 over I means 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. It's a decreasing sequence. Decreasing sequence, so that means we can bound it by an integral of 1 over x dx. And we did that, and the answer was ln. And so what happens here is we can simply say that all of this is nothing more than an upper bound of Hn, which is the nth harmonic number, which is the summation of a harmonic series of n terms. So therefore, this is the harmonic number. But the harmonic number is approximately ln n. We did that in class. Okay, so now we have 2 times n plus 1 ln n. And of course, if we change this, use the change base rule, and we change base rule, we can say ln n is equal to log of n, log 2 of n, over natural log of 2. And that natural log of 2 over 2 becomes 1.38. Okay? So, when we simplify all of this, we get a very nice result. I put it in bright yellow, 1.38 n log n. That's the result. That means that on average, with every pivot going into any location is equally likely, the number of comparisons you expect to get is about 1.38 n log n, which is remarkable considering the fact that the best you can hope to get is what? N log n, NLGN. So this is about 38% worse than the best possible case. This is with completely random numbers. So the result of this is that the average case of quicksort is the same as its best case. So remember that, the average case of quicksort is the same as its best case in terms of complexity. But remember this also, its worst case is as bad as n squared, which is as bad as insertion sort in the worst case or bubble sort. Okay? That's it. All right. I'm running late, and I can see the other professors giving me angry looks over there, so I need to leave. All right.